Before I get into the details of the history of the electric fields and the magnetic fields and the electromagnetic waves, I'd like to take a moment to go into a little bit about why I ended up making this video. See, I was writing a video on the physics of the Faraday cage, and I realized that I need to use electric fields to describe it. Then I discovered that Faraday had actually created the idea of electric fields for that very purpose in 1837. Now, I'd known that Faraday had created the idea of magnetic field, which he called lines of magnetic force, in 1831. And I knew Faraday had extended that idea to lines of electric force, or electric fields, before 1846, when he told people about the wild idea that maybe light was a vibration of these lines of force. But I didn't know the details of how and why he created electric field lines. The more I looked into it, the more profound it became. Lines of force, vibrating lines of force in space, well, that's the backbone of physics. Magnetic lines of force around magnets seem logical if you look at iron filing, but electric lines of force and electromagnetic waves, that took a truly unique brain. So for that reason, I wanted to make this video where I go over all the ways he made these different fields, what he got right, what we think he got wrong, and why he was so universally hated at the time. A word of warning. Most of my videos and my new book, The Lightning Tamers, which I have important news about at the end of the video, have about 80% personal stories to 20% science. But this video is the reverse, or about 80% science to 20% personal stories, because I want to go in a deep dive into the physics. Ready for a hardcore physics Faraday style? Let's go!
Electricity, electricity.
I'd like to begin on July 4th, 1831. That was the momentous day when 39-year-old Michael Faraday quit his job attempting to manufacture high-quality lenses for the British government. He had worked on it for 10 years and felt that his only results were his own nervous headaches and weakness. Scientists now think that quitting saved his life, because working with the heavy metals in those glasses actually was poisoning Faraday, which caused severe health problems for Faraday for the rest of his life. Glassmakers typically died in their 30s in the 1800s. Faraday didn't know about all that. He wanted to quit because he wanted to focus on pure science for science's sake. 8 weeks later, on August 29th, 1831, Faraday started a new section in his laboratory notebook with a hopeful title of Experiments in the Production of Electricity from Magnetism. After all, Faraday's friend, André-Marie Ampère, had demonstrated the current-carrying wire in the shape of a pancake, or a coil, acted like a bar magnet some 10 years earlier. And it just made sense to Faraday that if electricity could make magnets, magnets could also make electricity. But how? Faraday had conducted several experiments with no luck, until he remembered that a fellow Englishman named William Sturgeon had found that an electrified coil wrapped around insulated iron made a far stronger magnet, or magnet made with electricity, than one wrapped around glass or air. Faraday thought that if iron makes a stronger magnet, maybe iron could help transfer electricity from one coil to another. For that reason, Faraday wrapped two separate coils of wire on a single iron ring, with the hope that the magnetism from one coil would transfer onto the iron and make it magnetized, and then cause current to flow in the other coil. However, even though Faraday put a very strong current in the first coil so that it was a strong electromagnet, the second coil had no current. Frustrated, Faraday disconnected the battery, and an amazing thing happened.
And in the instant he did so, a current flowed in the secondary coil.
Then nothing. When he plugged in the battery again, the needle twitched again in the other direction. Then nothing again. Faraday repeated this experiment over and over again, and he found that the second coil would get current induced in it only when the first coil was being charged up or discharged. When it was flowing steadily, nothing happened, even if it had great current inside it. In other words, you only create current in a separate coil when the first one's magnetic strength was changing. Now that Faraday knew the trick for creating current, he pulled a very strong magnet out of a coil of wire and pushed it in again. When the magnet was moving, the compass moved too, meaning that a magnet created current without any battery needed. As electric induction was the term for moving charges without touching, Faraday called this Magneto-Electric induction. And he then made a law of induction, which he declared was very simple, although rather difficult to express. It was in order to express this law of induction that Faraday came up with the idea of magnetic fields or magnetic lines of force. Now, for centuries, people had noticed that if you sprinkle iron filings around a bar magnet, it creates patterns. And after the discovery of electromagnets, it was found that current-carrying wires could make similar patterns. But before the discovery of magneto-electric induction, there wasn't really a need to use magnetic fields for anything or even give them a name. Faraday went even further, however, and stated that these magnetic lines of force were always present around magnets and around current-carrying wires. The iron filings just made them visible. Moreover, Faraday decided that current is created or induced when the lines of force are broken or cut by a coil of wire. Think about pushing a bar magnet into a coil of wire. As you push the magnet, imagine the magnetic field lines passing through the coil. Or if you turn on or off an electromagnet, imagine the magnetic lines appearing or disappearing and cutting through the neighboring coil. Faraday felt like these disturbances in the force, not to get too Star Wars about it, that created the current in the coil. To recap, Faraday said that bar magnets and current-carrying wires have lines of magnetic force around them, and that you can tell that they do by putting iron filings around it to see the magnetic lines of force. Moreover, if a coil of wire cuts through these magnetic lines of force, a current is induced in the coil of wire. Faraday even imagined that the north and south of a magnet will be attracted to each other because their magnetic lines of force combine. And a north and a north, or a south and a south, will repel because their magnetic lines of force push against each other. At the time, had very little interest in describing magnetic forces as the pushing and pulling of invisible lines of force. But as a trick to explain magneto-electric induction, it seemed like a good idea, and people were very interested in induction. Supposedly, Faraday's discovery was so popular that the Minister of Finance and future Prime Minister named William Gladstone dropped by the laboratory to see it firsthand. When Gladstone asked Faraday about its uses, Faraday replied, "I know not, but I wager that one day your government will tax it." If this really happened, this comment is prescient, as all non-solar generators use spinning electromagnets next to coils to generate electricity. And yes, the government does tax it. Although Faraday could have easily profited from his newfound fame, he was a quietly religious man whose religion, called the Glassites, later called Sandemanians, believed that the accumulation of wealth was against the will of God. Faraday took this a step further and also rejected the adornment of honors and insisted on being plain Michael Faraday to the last. Meanwhile, Faraday's discovery of magneto-electric induction appears to have opened the floodgate of discovery, and Faraday published paper after paper after paper after paper on experimental researches in electricity. In 1837, for his 11th paper in 6 years, Faraday decided to re-examine old experiments with his new knowledge of physics, especially the work from 1768 from Charles Augustin Coulomb of Coulomb's law fame, who found that all charges on a conductive material will be only diffused over its surface and does not penetrate into its interior parts. Faraday then recreated all of these experiments and found, like his predecessors had found, that conductive materials will have all their charges on the surface and the inside will be protected from all electric forces. Faraday even built a giant cage or cube that was large enough to live in. He found that he couldn't see any electric effects from the inside, but how did it work? Inspired by his definition of magnetic lines of force, Faraday started imagining inductive lines of force, or lines of electrical force that move at a distance, emanating from charged objects and around changing magnetic lines of force. Like magnets, inductive lines of force, or electric fields, combine to make opposite charges attract and push against each other to make like charges repel. Unlike magnetic lines of force that only work on other magnets or on certain materials like iron, inductive lines of force, or electric lines of force, work on all objects, even if they're neutral, because as Faraday learned from Benjamin Franklin, even neutral objects that we can see aren't 100% neutral, but instead have equal amounts of positive and negative charge. However, what happens to an object in an electric field depends on what kind of object it is, conductor or insulator. Now, conductors are the easiest to explain. See, conductors are conductors because they can easily conduct electricity. For that reason, the electric field lines can push the charges in the conductor until the charges balance out the external electric field. If there's any remaining electric lines of force left, the charges would be pushed to move until there wasn't. In fact, one definition of a perfect conductor is a material for whom any net charge will reside on the surface and the electric field inside is zero, even in the presence of an external electric field. This is why a Faraday cage protects you from the external forces. It's because the electrons in the metal move to cancel out the electric field, leaving you safe inside. Insulators, on the other hand, have their charges more stuck in place, so they can't move very far. So they don't tend to cancel out the electric field. However, just because they don't cancel out the electric field doesn't necessarily mean that they have no effect. In fact, Faraday initially thought that not only do insulators affect the electric field, they're actually required for the electric field to travel in space, writing that all electric forces never occur except through the intermediate influence of the intervening matter. What Faraday meant was that the molecules of air, or the ether that they thought was invisible and everywhere in all material, including vacuums, or whatever the electric field was transferring through, lined up and sort of propelled the electric field forward. Because he had this thought, he naturally wanted to test whether certain materials had more of this propelling electric field force than others. And he did several experiments, including testing out how much charge a parallel plate capacitor could hold depending on the properties of the insulating material between them. In this manner, he found a certain class of insulators would have a huge effect on the amount of charge on parallel plate capacitors, and he called those kinds of materials dielectric, to express that substance through which the electric forces are acting. Faraday also postulated that in these dielectrics, the charges are sort of twisting, like the magnetic domains in a magnetic field, where how much the dielectric affects the electric field depends on the dielectric's specific inductive capacity. We currently think that dielectrics will bend the electric field depending on this capacity, also called the dielectric constant, but do not propel the electric field and are not needed for the electric field to travel in a vacuum. If this is all sounding a little strange and possibly unscientific, imagine how the scientists in the 1800s felt. They thought he was basically bonkers. For example, in 1855, the royal astronomer Sir Airy piped up with, "I declare that I can hardly imagine anyone who practically and numerically knows physics to believe anything so vague and varying as lines of force." The more Faraday thought and debated about it, the more convinced Faraday was that the lines of force were real and very important. And that brings us to Faraday's frankly crazy idea that maybe light itself was a wave of these lines of force. Now, in order to talk about that, I think I should take a step back and talk a little bit about something called the polarization of light and what they knew about it at the time, because it was very influential for his paradigm shifting idea that light was an electromagnetic wave. See, for many, many years, people knew about a strange crystal called an Icelandic spar that would split light not into various colors, but into two identical images. However, if the crystal was used to look at light reflecting off a low angle, or the glare, then there was only one image. This was examined by a French engineer named Etienne Louis Malus, who decided in 1811 that light had two of what he called polarizations, where the glare only reflected one of these polarizations, and the Icelandic spar split the two polarizations different amounts. Malus even came up with a theory about the angle of reflection to get polarized light and the index of refraction of the material it was reflecting off of, but was stymied by the poor quality of glass available to him. This equation was then found 4 years later by a man named Sir David Brewster, which is why this angle is called Brewster's angle. Then in 1828, a geologist named William Nicol used his methods that he had created to make very thin pieces of rock and crystal for his geology studies, to fashion two prisms of Icelandic spar together in such a way as to create a polarizing filter. Nicol's polarizing prism would only have one image, as it refracted one of the polarizations out the side of the prism. Therefore, if you look at glare through this prism, you can block out the light if you hold it at the right angle and let all the glare through it if you twisted it. It's kind of magical. By the way, polarizing sunglasses use this same process. That brings us to July of 1845, when a 21-year-old Irish student named William Thomson asked Faraday if he had ever studied if or how polarizing light changed when light was going through a transparent dielectric. Faraday was intrigued and therefore shined bright lamplight off a glass at Brewster's angle to polarize it, then passed the light through a piece of heavy glass with a high dielectric constant, and then through a nickel prism that was twisted to cancel out the light. On September 13th, 1845, Faraday was delighted to find that a large magnetic field across the dielectric would cause the polarization to change so that it could see the light through the nickel prism. Faraday crowed, "Thus is established, I think for the first time, a true direct relation and dependence between light and the magnetic and electric forces." Fun fact, it was this paper that Faraday switched from inductive lines of force to electric lines of force, which is a decidedly easier term to use. That is why in early 1846, Faraday came up with an even more radical thought. Maybe light wasn't a wave in the invisible, infinitely strong, all-pervading ether. Maybe light was a wave of these electric, magnetic lines of force. This wasn't a brand new thought for Faraday. Way back in 1832, a few months after creating the idea of magnetic fields, Faraday came up with the idea that magnetic action is progressive and requires time. And I see reason for supposing that electric induction is also performed in a similar progressive way. He even came up with the idea that diffusion of magnetic forces from a magnetic pole is like the vibrations upon the surface of water, or those of air in the phenomenon of sound, and most probably to light. In other words, way back in 1832, Faraday came up with the idea that magnetic forces and electric forces take time to travel in air and can travel in waves in the air, just like sound travels in air and light travels in air. However, this idea was so radical that he was loath to say it without experimental proof. Therefore, Faraday put it in a secret letter to be held in the Royal Society's storage box, so he could prove that he had the idea first, if someone else experimentally proved it before him. It was only released to the public in 1937. However, before 1845 or early 1846, Faraday, like every other scientist who believed that light acted like a wave, thought that there was an invisible fluid everywhere called the ether that was the medium for the light to vibrate through. However, his experiments with the polarization of light in 1845 combined with his old thoughts from 1832 that electric forces and magnetic forces take time to travel through space, and you can imagine a vibration or wave of them traveling through space, made him start to think that you could just give up the ether. He even wrote in his diary, so inclined to dismiss the ether. Of course, that also made him have to give up the idea that electric forces needed the ether of space to propel the electric force. And he wrote, I believe that when there are intervening particles of matter, they take part in carrying the electric force through the line, but that when there are none, the line proceeds through space. Faraday was still internally debating these ideas when on April 3rd, 1846, the speaker at the Royal Society had a bout of stage fright and skipped out on his speech minutes before the talk. That is how Faraday ended up giving his one and only unprepared lecture of his career. Justifiably nervous, Faraday started his talk by giving a warning that he was just expressing the vague impressions of my mind without sufficient consideration. With that caveat out of the way, he asked his audience to imagine a simple scenario. Imagine two objects, A and B, that are distant from each other and under mutual action, and therefore connected by their lines of force. He then asked the audience to imagine if one of the objects moved, and how that would lead to a vibration of the lines of force, which would then vibrate the second object. Then Faraday said what I consider one of the most influential and radical postulates in all of science history. Quote, the view which I am so bold as to put forth considers, therefore, radiation, i.e. light, as a high species of vibration in the lines of force. It endeavors to dismiss the ether, but not the vibration. Then, after that profound truth, Faraday added what we now think is a mistaken thought, that because of polarization, light must be a back and forth, or longitudinal, or what he called a lateral vibrations. Let's take a moment and pause and think about what a truly momentous and outside-the-box thinking went into this statement. Back in 1831, Faraday created the idea of magnetic lines of force, or magnetic fields, to explain how magneto-electric induction works, and also found that they could be a way of envisioning how magnets attract and repel. Months later, he wrote a secret letter that magnetic and electric forces might take time to transmit and could make waves in space. 5 years later, in 1837, Faraday came up with the idea of inductive lines of force, or electric lines of force, to describe how a metal box can protect you from the electrical effects on the outside of the box, and also realized that insulators could alter an electric field and named a set of insulators dielectrics for their ability to affect the electric field. Finally, in 1846, Faraday came up with the bizarre idea that maybe light itself is a vibration of these electromagnetic lines of force, and that you didn't need the ether. And Faraday did this, and way, way, way more, without any math, as he had basically no math skills, except possibly a little bit of algebra. Although people honored Faraday for his experimental results, they weren't as fond of him for his theoretical constructs, especially this last crazy one about light. Therefore, Faraday's vague impressions of my mind were almost universally rejected by scientists. The lines of force seemed unscientific, physicists liked theories with math, and everyone knew that the ether was real. It seems like most of these ideas, especially the one about light, would have just faded from view if it weren't for the work of a young Scottish mathematician and physicist called James Clerk Maxwell. Maxwell decided he liked almost all of Faraday's ideas, but wasn't particularly fond of the idea of giving up the ether. So he just put it right back in, which made Maxwell, although still very controversial, at least a little bit more appealing to scientists at the time than Faraday. Maxwell then started writing paper after paper about Faraday's lines of force, culminating in his magnum opus, A Dynamical Theory of the Electromagnetic Field, published in 1864, which contained a primitive form of what is now called Maxwell's equations. In this paper, unlike Faraday, who thought that light was a longitudinal wave, Maxwell felt that the only way to have the properties of polarized light was if the disturbance at any point is transverse to the direction of propagation. In addition, Maxwell mathematically determined that as a moving charge is a current, it would create not only an moving electric lines of force, it would also create a magnetic field or magnetic lines of force. Therefore, a vibrating charge would create a vibrating electric lines of force and vibrating magnetic lines of force, both of which travel at the speed of light. Maxwell called this a wave in electromagnetic fields. He called them fields because it has to do with the space in the neighborhood of the electric or magnetic bodies. Soon, all these lines of forces were renamed fields. Electric fields, magnetic fields, even gravity fields. And we've been using those terms ever since. Now that I've gotten in more detail about the origin of the electric fields and the magnetic fields and the electromagnetic waves, it is finally time to do a deep dive study of the physics of the Faraday cage, including why it even works with those holes in it. And that is next time on The Lightning Tamer. Don't leave, I have exciting news about my book, The Lightning Tamers, about the history from 1580 to today of the scientists who discovered electricity. Is available for pre-order on Amazon in ebook form, paperback form, and hardback form, as well as from your local bookstore. There is a link down below. If you're not sure whether you want to pre-order the book, which that would be crazy, of course you want to pre-order the book. But if you're still not sure, you can go to my website, www.kathylovesphysics.com, and get the first 3 chapters in PDF form for free and check it out. How great is that? Big thanks to my patrons. Thank you, patrons. And remember, stay safe and curious. Although Faraday could have easily profited from his newfound fame, hard to say, in 1855, the royal astronomer Sir Joseph Airy. Hey, I got his name right.